The most fundamental unit of computer memory is the bit. Each of these bits is stored in a memory cell that can switch between two states, 0 and 1, like a switch that goes on and off. Computers are made of devices that can flip between the states of 0 and 1. Traditionally, we have gone from using relays, vacuum tubes, to the transistors, which are the most prevalent devices we use today. The essence of all these devices is that they can switch between two states. Now that we have devices that switch between the states, we can construct logic gates. Let's construct an ordinary OR gate and feed the output back to one of its inputs. First, if both the inputs are set to 0, 0 or 0 will give the output 0. Say we switch the input A to 1 now, the output becomes 1. This will loop back into input B such that both inputs are now 1. 1 or 1 is still 1. There is no change in the output. If you again change the input A to 0, the circuit still outputs 1. Now we have a circuit that records 1, except that now we have a problem. This change is permanent. Since the output is 1, no matter the input, there isn't a way to change the output to 0. Now we will take an AND gate with its output looping back into its input again. If we start with both inputs at 1, the output will be 1. 1 and 1 outputs 1 forever, unless you change A to 0. Since it's an AND gate, now the output will change to 0. The output will loop back to 0. Again, we face the same issue as the previous circuit. The output now being 0 cannot change back to 1 no matter what the input. So, we have found a way to record 0 in a circuit and a way to record 1 in a circuit. To make this a useful piece of memory, we have to combine these two gates to make what is called an AND OR latch. We got a set input that sets the output to 1 and a reset input that changes the output to 0. If set and reset are both 0, the circuit outputs whatever was last put in it. In other words, these latches can remember a single bit of memory. This is called a latch because it latches on to a particular value and stays that way. Since having two wires for input is a bit confusing, we can modify the circuit a bit such that we have a gated latch. A gated latch will have a wire called data input that we can set to 0 or 1 to input a bit, and another wire, write enable, to open the latch for modification and to close the latch to store the bit. Starting everything at 0, let's change the data input wire to 1. Nothing happens because the write enable wire is off. The write enable wire is a lock to the gate. When it's locked, you can't change or rewrite what's inside the latch. Now let's open the gate by turning the write enable wire to 1. Now we can change the input to 1, and yes, the data inside the latch successfully changes. So the output is 1. If we turn off the enable line, we can store the data inside the latch and it's now prevented from being rewritten. As long as the enable line is off, no matter how we change the data input, the output remains unchanged. Now, if we turn the enable line on and set the input data line to 0, the latch is set to 0 and the output changes. Enable line off, the value is locked in the latch. A register consists of a group of latches, with each latch capable of storing one bit of information. An n-bit register has a group of n latches and is capable of storing binary information of n bits. The latches hold the binary information and gates control when and how new information is transferred into a register. In short, a processor register is a quickly accessible location available to a computer's processors. A register can hold an instruction, a storage address, and any type of data like a bit sequence or individual character. Processor register is one among many data holding places such as L1 cache, L2 cache, L3 cache, RAM, SSD. These registers are part of the computer processor. Register memory is the smallest and fastest memory in a computer. It is not a part of the main memory and it is located in the CPU. A register temporarily holds frequently used data, instructions, and memory addresses that are to be used by the CPU. They hold instructions that are currently processed by the CPU. All data is required to pass through registers before it can be processed. Registers are normally measured by the number of bits they can hold. For example, an 8-bit register, 32-bit register, or a 64-bit register, or even more. A register must be large enough to hold an instruction. For example, in a 64-bit computer, a register must be 64 bits in length. In some computer designs, there are smaller registers, for example, half registers for shorter instructions. Registers hold a small amount of data, around 32 bits to 64 bits. The speed of a CPU depends upon the number and size of the registers built into the CPU. Almost all computers load data from a larger memory into registers where it is used for arithmetic operations and is manipulated or tested by machine instructions. Manipulated data is then often stored back into the main memory. When a computer program accesses the same data repeatedly, this is called locality of reference. Holding frequently used values in registers can be critical to a program's performance. Registers are the essential component in computers because CPU cannot directly access data that is stored in the memory and it must be first passed through the registers. Whenever CPU gets the data or executes the instruction code, a cycle known as the fetch, decode, execute instruction cycle takes place. The computer needs processor registers, otherwise known as accumulator, for manipulating data and an address register for holding memory address. The register holding the memory location of the address of the next instruction that is to be executed when the current instruction is completed is called program counter. An instruction register is the register that holds the instruction currently being executed, encoded, or decoded. It is useful to note that some instructions specify registers as part of the instruction. For example, an instruction may specify that the contents of two defined registers be added together and then placed in a specified register. To see how registers are used, we will need to talk about addressing modes which define how machine instructions are used and access memory. Let's see that in the next episode.